Hello, everyone. I'm Yelo from Argonne National Lab. I'm an assistant computational scientist. Today, I'm going to talk about OpenMP offload optimization guide, typically beyond kernels, and all the lessons I learned from QMCPACK. So I'd like first to thank the ECP, the exascale computing project supported by the Department of Energy, and also would like to thank the QMCPACK ECP developer team, and also the ECP Solve team, which helped me with a lot with OpenMP. So just one slide about QMCPACK. It is a modern high-performance open source quantum Monte Carlo simulation code. It is written in C++ and designed with object-oriented programming and meta-programming with templates to achieve the best flexibility and computational efficiency. It is a real-world application. All the examples in this presentation reflects the OpenMP use patterns inside QMCPACK, although they are stripped down to help you understand in this talk. Last thing is most of the OpenMP explorations, prototyping, we do it via mini-QMC, a QMCPACK mini app. So let's start talking how to do the optimization. There's a story that you've heard many times about porting experience for GPUs. That is, you did a lot of work and then you realize why I'm spending more time actually. So the measured host time and overall work log time goes up in the application, but when you throw in a profiler and it indicates the GPU activity is low. This is because the characteristic of accelerators have many limitations and programmers need to be care about. And when you program using OpenMP, you're also limited by those characteristics. So when porting with OpenMP, the overall goal is to minimize the OpenMP overhead on top of those vendor programming models. So it has many aspects. One is inside the kernel. So OpenMP offload regions are transformed, the source code are transformed into kernels and queued and executed by the device. That needs to be efficient. Second is beyond kernels, that OpenMP abstraction adds additional overhead. So we would like to minimize that. So for application developer, we have to adopt best practices in user code to help that. And also we need a good OpenMP compiler or runtime implementation to fully achieve minimized overhead. So this talk will focus on all the optimizations we can do beyond the kernel. So before talking about other optimization, I'd like to mention that we have applications needs to be careful about the programming styles as well. So it enables portability in many cases. So OpenMP offers two programming styles actually. Although that mostly OpenMP is a directive-based programming model, it also have APIs. When you use a directive, like the left-hand side example, you have a target region. This is target enter data, basically to allocate the data on the device. And on the right side is the API. You directly invoke the target alloc host functions to allocate the device of memory. So on the left side, it has the advantages. There's no side effect when you turn off your flag in the compiler, OpenMP offload flag in the compiler. And even if you turn it on, you can fall back to host for debugging by just leveraging the OpenMP 5.0 feature. It's an environment variable to disable the offload. It has disadvantages that it is less verbose for people. When you program in OpenMP API, the prompts are, you have the full explicit device control. The disadvantages, it's an API, so you have to protect it with pragmas to avoid compiling them when OpenMP is off. And also it is hard to design a fallback logic to run things on the host. So QMCPACK developers found the left side ones more preferable in real applications. So let's start the optimization guide. So first is the simple example. On the right side, the first one is a single target map and array, a target region with a map of array. You do some operations on the accelerator. This is a textbook example, but it's not good for performance in real applications, because when the map happens before and after the offload region execution, that the runtime needs to allocate memory for array on the device and deallocate after. These operations are orders of magnitude slower than that you typically do with malloc and free on the host. So how to avoid those costs is OpenMP offers the target enter data and exit data directives to help you. You can pre-arrange the allocation that at performance non-critical area of your code ahead of your actually offload region. So this helps bypass those allocation deallocation cost at every call to the offload region. And in certain runtimes, those operations may also blocking asynchronous execution of other offload regions. So it's critical to your performance. So pre-arrange your allocation deallocation outside your frequently called target region. So QMCPACK is C++ code, so we can even do better with abstractions in C++. That is to create an OpenMP allocator wrapping all the target enter data, exit data inside this customized allocator. This allocator can be used with regular container classes, std vectors, to vector in C++ code. So in the design of our OpenMP allocator, we actually template on top of a host allocator. It can be a regular stud allocator, or it can be a customized one which you can handle like memory alignment, and you can even add registration, registration of this host memory into the accelerator memory space for maximum transfer performance. So if you program in CUDA, you can add the CUDA host register inside your host allocator. Once you get those right, there's additional tips for get best performance. So the simple case on the right shows a very common use cases in an offload region. You need to access some scalars like A, B, C. You might thought, oh, I need those ones on the accelerator. I must map them. But most compilers implement those explicit mapping as allocating memory for it and transfer the data and deallocate. So I've mentioned deallocating is very expensive. Now you are transferring like 4 bytes of 8 bytes data. It's also extremely inefficient. So how to avoid that? Basically, you don't need to add this map because since OpenMP 4.5, scalars are first private by default. So compilers can pack them as kernel argument, and there's no allocation and explicit transfer involved. So leverage that feature to maximize your OpenMP offload performance. So apart from what we can do in the source code, the runtime also helps. A good implementation of OpenMP offload runtime can leverage the vendor-supported concurrency computing models. For example, for NVIDIA GPUs, CUDA has these CUDA streams for asynchronous computing, and a good OpenMP offload implementation like IBM XL and LVM Clan can take advantage of that. On the right is the offload region, target offload region that already used with the optimization guide I mentioned earlier. Now this single target region will trigger 3 operations when offloading. First, it will transfer the data of array to the device, and then it will execute the kernel, and then return by transfer back the array from device to host. All these operations can be incurred into a CUDA stream and put a single synchronization in the end. So this adds additional efficiency to our to the offload. So CUDA stream is one of the features. Other vendors support similar features. Let's see how it behaves in the real time in applications. So here is a NVProf output, NVVP visualization of the NVProf result of mini QMC. So within this single OpenMP offload region, that OpenMP runtime transform the transformed offload region into a bunch of calls to the CUDA driver API and also launching the kernel. So you notice that I point out all those driver API calls that asynchronously, which are the host to device and kernel launch and device host. They all spend a very little amount of time. So the asynchronous behavior are all engaged. And at the end, because my offload region is still blocking, that you see this CUDA stream synchronized at the very end. So there's no, it's basically close to what I would like to program directly in CUDA. So OpenMP offload overhead is really, really minimized. In this example, I'd like to emphasize the kernel is not a huge kernel. You might think that I used a huge kernel to amortize the launching overhead. Actually not. This kernel is only about 20 microseconds. So now since we have a single OpenMP offload region very efficiently implemented, now we can leverage concurrent execution and data transfer, which is a technique we mentioned very frequently in asynchronous offload. Partly due to the hardware limitation that the runtime offers a way to reduce those overhead from the hardware restrictions. So OpenMP runtimes like IBM XL and LVM can send the OpenMP offload region into independent CUDA streams. By this feature, we are able to execute target regions concurrently, just by wrapping them with OpenMP offload, OpenMP thread. So on the right side is an example. You see that I have an outer loop which is distributed over threads, and within each thread, there are offload computations. This is reflects the real world QMCPACK use cases. So by doing this, actually operation from different threads, the offload from different threads can overlap with each other. I'd like to show you with the profiler result. So the concurrent execution is reflected by MVVP in this mini QMC execution as well. You will see that I'm running with 8 OpenMP host threads. And that's why in the profiler outputs, you see 8 CUDA streams. And you notice that the stream 18 and stream 21 are overlapping the data transfer and computation. So the first red box. And on the right red box, you even see that concurrent kernel execution and also overlap with data transfer as well, because my kernels are very small. When the GPU realizes there are additional available resources for other kernels to execute, it will try to run more things. Okay. So this, in addition to that, there are more concurrency we can leverage from OpenMP. That is using the tasking to coordinate the host and offload computation. So when we put in a very big application, that we need to enable a feature complete experience for users. That's why we cannot put, it's impossible to put every feature to an accelerator in a very short period of time. So for this reason, we would like to have partial of the application running on the accelerator and partial of them still running on the host. We know that when the accelerator is executing things, the host side is typically idle. So we would like to add some work, the CPU side tasks to those idle CPU resources. So OpenMP tasking offers such opportunities. So start from the previous example. Now within a thread, we not only just do a target region offload, we also have other CPU tasks, because the target can be transformed as an asynchronous task with this no-wait clause. We can have the target task and regular CPU tasks all coordinated with the tasking runtime. So in my example, I have a target no-wait first launching a GPU task, then it returns immediately. So with the then on the second is a CPU task, the host task one. It's completely independent and non-blocking. And then followed by a CPU task, which depends on the result coming out of the target task. And at the very end, I just put a OMP task wait to synchronize all the tasks. Just to be careful, this way of doing tasks the performance heavily depends on the compiler runtime implementations. So there are very nice features as OpenMP 5.0 and beyond gets published and implemented in compilers. I list some of them beneficial in the view of QMCPACK developers. For example, the meta directives and declare variant functions. Those really help better organize the source code and reduce duplications in the application. Duplications. When we port in GPU code for multiple vendors, sometimes we can't really avoid specialization. So with these like variant functions, we can restrict the specialization to very limited areas and keep the upper level code clean. There are also the detached task feature, which helps the composability with other asynchronous runtime systems. And also the interrupt object feature helps exposing the vendor native queues streams to allow programmers to directly interact with the vendor native runtimes for close to metal experience in programming OpenMP. And also there are OMPT and OMPD support for profiling and debugging tools, which is very nice for developers. So here is the example of detached task we would like to write. This example is to asynchronously call cuBLAS without explicitly waiting the CUDA runtime. So on the right side is the sketch code. So the first detached task will launch a cuBLAS call and also enqueue a callback function to the CUDA runtime to signal back OpenMP runtime, a tasking runtime when the task, the asynchronous cuBLAS call is completed. It follows by a target no wait, a target task we program in OpenMP to execute following the first one. And then there's a second detached task calling another foo-blast call. And in the end, we use OpenMP task to synchronize all of them. So there's no directly call to the CUDA stream wait or CUDA device wait to wait for the CUDA runtime to return. So this maximizes the efficiency and compose vendor libraries, calls, and OpenMP asynchronous computation. So detached task is a list feature for 5.0 specs, but we are still waiting for actual compiler implementation. Beyond that, there are many features actually needed for OpenMP applications leveraging OpenMP target offload, which are not part of the OpenMP spec, but highly needed or highly required feature to be useful, to make OpenMP useful for applications. So QMCPACK developers struggled with those features in 2019, and luckily there are a lot of improvement in 2020. So I'd like to mention them. So this is the tracking table of mini QMC for different vendor compilers and different vendor and open source compilers and different devices, including NVIDIA, AMD, and Intel. So those features are like math functions. Elemental math functions cannot be avoided by most applications in simulation world. Second is complex math arithmetics. Quite a wide range of applications actually need that feature inside the OpenMP offload region. Some applications also need declared target static data to have some global pre-arranged data set. And in addition, the linking of static archives with device code inside is a needed feature for writing big applications. Then the last one is the multi-stream concurrent execution. Like QMCPACK is sensitive to that, so that's also needed. So luckily, the situation is a lot better today, and I hope they are improving over time as well. So it's very promising to use OpenMP in real applications. So summary. So this talk, we cover the topics application developer needs to pay attention to performance that is beyond the kernels, mostly in the runtime, and how to minimize all sorts of overhead due to OpenMP. And I've shown that this overhead can be simply minimized and close to nothing compared to the actual native runtime cost. And there are many simple patterns can be adopted by OpenMP offload feature users to have significant performance gains. So in addition, that task level parallelism can be considered. So they become essential for accelerator asynchronous computation. Last, in 2020, the compiler and OpenMP runtimes in the implementation is significantly improving and allows production use of OpenMP. So here's the end of my talk.